Let's solve this quiz. I know that your quiz is simpler than what's here. So we're not going to do part A. We're going to do part A later. First, let's find part B. If a thin infinite wire is passing through the center of the toroid, find the mutual inductance between the wire and the toroid. How was mutual inductance defined? If I had two loops, when I run current in one loop, this is going to create a flux through the second loop. And that flux is going to be proportional to current in the first loop. So mutual inductance was defined as the total flux in the second loop as a function of the first loop, and the proportionality constant was called the mutual inductance. So what do I need to do? I need to calculate the magnetic field created by the wire and see how much flux it generates through the toroid. That's it. Okay? How do I calculate the magnetic field created by a wire? Ampere's law. Excellent, right? That's the simplest thing. That's the thing we have actually done many, many times. So if I take an ampere loop like this at radius r, so if I look at the system from the top, here is my current source I, and here is my ampere loop at radius r. B dot dl is mu 0 times I in. By symmetry, B is parallel to dl all on my ampere loop. So this is going to be 2 pi r times B magnitude. How much current is passing through my ampere loop? If the current is only in the wire, which is the thing I'm interested in, then it must be just I. So B is going to be mu 0 I over 2 pi r. How many of you obtained this result? I'm assuming almost everyone. If they wanted to show some effort, they wrote this down. Okay. So what do I need to do now? I need to calculate how much flux is generated by this magnetic field. Now this magnetic field direction is circling my wire, right? With the right hand rule sense. And all of this magnetic field is basically, well, not all, some part of this magnetic field is going inside the toroid. So what do I need to do? I need to calculate what's the total flux inside my toroid. All right? And let's do that. Let me look at the system from the side. From the side, what does the system look like? There is this wire running the current, and at a distance a away, I have this square going to B, and the other side is B minus A. Now what's the flux through this square? The flux through the square, can I just say it's the area of the square times the magnetic field? No, why not? Because the magnetic field inside is actually changing. So what do I need to do? I need to integrate. Excellent. So let's do that. Let me take a section of thickness dr and calculate d phi through that section. D phi is going to be, magnetic field is uniform in that small region. It's exactly what we found, mu 0 I over 2 pi r. And the area of this cross-hatched rectangle is B minus A times dr. So what's the flux through the square? It's going to be integral d phi. If I write it more clearly, mu 0 I over 2 pi r B minus A dr. What are the limits of my integration? Where do I start integrating from? From A and go all the way to B. So my flux through this square is going to be from A to be, let me even take out the constants, mu 0 I over 2 pi b minus a is a constant. I have integral dr from a to b 1 over r dr, and this integral is just ln. So mu 0 I over 2 pi b minus a ln b over a. Now this is the flux through one square. If I actually want the flux through the whole toroid, what do I need to do? I just need to multiply it by n, because I have n turns of wire along the toroid. So I can say flux of the toroid is n times flux of the square. Let me write it in another way. Mu 0 n b minus a over 2 pi ln b over a times I, and this is what I'm looking for. This is my mutual inductance. All right? Any questions? Any comments? How many of you reached a similar result? Okay, we're not doing too bad. But in a couple of weeks, I think all of you should get there. Okay, you should be able to calculate this. Now, how about the mutual, instead of mutual inductance, how about the self-inductance? How do I calculate the self-inductance? Now, I don't have to think about the wire now. What I'm interested in is if I'm running a current in the toroid, how much flux it's generating through its own center. All right? So, how can I do that? First, I must think a current I is running through the toroid and find its magnetic field. And secondly, calculate phi through the toroid. So let me call this I toroid. That's all I need to do. Let's do it. It's going to be very quick. How do I calculate the magnetic field inside the toroid? Inside toroid. Now, if I look at the system from the top, if I take a cross section, what does the toroid look like? The toroid looks like two circles, right? And the wires of the toroid, they are going to carry current in some way. I did not draw it, so I don't know which way. But if I take a cross section, all the wires on the inner surface of the toroid will carry current one way. Let's say coming towards me, while all the wires on the outside must be carrying the current the other way, right? I'm getting lazy about that. The wires are probably much more dense than that, but okay. Now, how do I calculate magnetic field inside? Well, it's not too hard. I take a nice ampere loop of radius r. So I'll say integral b dot dl is mu 0 times I in. Again, by just symmetry, B dot dl I can write as 2 pi r times B magnitude. But what's the total amount of current that's passing through my ampere loop now? It will be n times how many, all the windings of the toroid pass through my loop. So it will be n times what I called I toroid, right? Hey, this is very good. So B magnitude is mu0 n I toroid divided by 2 pi r. Do I need to calculate the flux of the toroid again? Do I need to do the integration again? Well, I mean, technically yes, but I already did it once, right? The magnetic field I found previously is not different from the magnetic field I found here. So it's not going to be too different. It's not going to change at all. Found by the same integral. So it's going to be exactly the same stuff, only I need to multiply it n by n. That's going to be my answer, mu0 n square B minus A over 2 pi ln B over A times I toroid. So this is going to be my self-inductance. All right? Is everyone happy? Towards the end of the term, no one seems to be happy. But let's continue anyways. So, I'd like to start talking about our last chapter today. Okay? We have around 5 lectures left, and that should be more than enough time for us to complete it. So what we're going to talk about now is Maxwell's equations and electromagnetic waves. What are Maxwell's equations? You may be excited about hearing this name, Maxwell's equations, Maxwell's equations. Well, okay, I'll write them down. And you'll see that maybe you remember them. Hey, this is Maxwell's, if you want, first equation. You know it by another name. What's this? Gauss's law. I'll write another equation. I've written this down once, but maybe did not stress its importance much. My rule about magnetic field was that magnetic field lines always closed onto themselves or they went to infinity. There were no magnetic charges. If I had a north pole and a south pole in a magnet, if I cut the magnet into two, I get 2 north poles and 2 south poles. I could not get just a isolated north pole or isolated south pole of the magnet. So if I write a similar thing for magnetic field, what should I find? If the magnetic field lines are never ending on charges, the total charge in any closed surface is apparently 0, because all the field lines which are entering this surface must be exiting that surface. They cannot terminate somewhere inside. So this is B dot dA is equal to 0. This is called Gauss law for magnetic fields. It's actually known by another name. You know, saying charge, everyone has heard about charge. Your grandmother has heard about charge. But instead of saying charge, if I say monopole, which exactly means charge, then that sounds much sexier, right? So how are we going to call this law? The other way to call this law is called no magnetic monopoles. By the way, how many of you watch the Big Bang Theory sitcom? Okay. So at the end of one of the seasons, I don't remember which one, they go to the North Pole to look for something. Do you remember something? They were looking for magnetic monopoles. So people have tried to find really if magnetic charges exist in nature. They have looked at absolutely everything, right? There is a huge satellite looking for magnetic monopoles that's orbiting the Earth. And people have looked for magnetic monopoles on the dust from the moon, on moon soil. Why do people keep looking for magnetic monopoles? And obviously we don't see them. That's the law. We wrote it down. We can't find them. That's why. The funny thing is that a brilliant physicist showed that if even a single magnetic monopole exists in the universe, then your electric charge must be quantized. It must come integer multiples of some unit charge. Which unit charge? The electron charge, right? So that's a fantastic proof. Okay. So we'll be very happy if someone finds a magnetic monopole. We will understand more or less why charge has to be always an integer multiple of electron charge. So people still keep looking for magnetic monopoles. However, as the present situation exists, there are no magnetic monopoles. Okay, that's why we write our equations like this. If somehow, just like gravitational waves were found this year, in the future, one day, if someone actually sees magnetic monopoles, we'll change our equations. We'll add a term to this equation. But right now, it seems quite clear, at least on this Earth, in this region of universe, even if there are magnetic monopoles, they are not around most of the time. Okay? Good. So let me write down another law. P dot dl is mu 0 I. This is Maxwell's third equation. But you know it by another name. This is Ampere's law. And how about this? E dot dl is minus d phi b dt. That's the Maxwell's fourth equation. And you know it as Faraday's law. So clearly, there are four equations here. None of them were derived by Maxwell. So how come, did Maxwell pay money to those people so that these are called Maxwell's equations now? No. Actually, by the way, that was a thing in the 18th, 16th century. You could pay a scientist so that the next thing he finds will be under your name. Do you know the L'Hopital rule? L'Hopital rule in calculus. L'Hopital didn't know any math. He gave money to someone, and your next theorem will be L'Hopital rule, and you still know his name. So I think that was money well spent. Now, the thing is, Maxwell was also a brilliant guy, and he said, hey, there is something wrong with these equations, the way they stand. So he thought of the following situation. So let me, come on. I hate when this happens, right? Settings. Let's hope that this works. here is what Maxwell said. He said, if I take a wire that's running some current I, and if I take an ampere loop around it, I know that B dot dl is going to be mu0 times I at each moment. But what about the following scenario? What if I really zoom in here, and instead of an unbroken wire here, maybe it's not really a wire, but there is a capacitor here, a small capacitor. So that the surface I'm interested in does not cross the wire at all. So there is no current passing through that surface. And the thing is, I can make this capacitor very, very small. The only thing I require is that the surface does not have any current passing through it. Now, I know from Biot-Savart's law that most of the magnetic field on this loop will be generated by currents which are far away, current pieces from which are far away, right? They will not care what happens exactly on the place where the surface crosses the wire. So even if there is a very small capacitor there, so that the charge is not passing through, but electric field is pushing the charges, I should still get the same magnetic field. However, Ampere's law tells me that no, it's only the current that's passing through your surface that matters. Okay. So how come B depends only on I crossing the surface? He said, hey, that cannot be correct. All right. There must be an other term in Ampere's law. Now, what happens? How can I run a current through a capacitor? If I'm running a current through a capacitor, the charge on the capacitor must be increasing all the time. Okay. If the charge, so basically the current here is dq dt. But if the charge is increasing in time, how about the electric field inside the capacitor? Electric field is also increasing with time. So I said, hey, maybe induction, how did we learn about induction? We said, if I have a surface through which magnetic field flux is changing, that generates an electric field. Maybe something similar is at play here. Maybe I should add a term. So this is going to be proportional to the electric flux through my surface. So maybe I should add a term into Ampere's law which takes this change in electric flux into account. So he calculated, and we can do the calculation, it's not a hard calculation. B dot dl is mu0 times I in. So he wanted to see how much, what's the proportionality constant between this change of rate of electric flux and B, and he saw that this is mu0 epsilon 0 times d phi e dt. So he basically said the following: for any surface, it's not only the amount of charges passing through that surface that create the the magnetic field, but there is also another term, epsilon 0 d phi e dt, which he called the displacement current. Now, the calculation here is not very hard, okay? And the important thing here is to be able to think about all this argument, saying that there must be something wrong with Ampere's law, because if I think of a capacitor, it fails, okay? So, Maxwell found this out. He called this displacement current. But still, do you think, I mean, correcting one equation gives you the right to all the 4 equations there? By the way, let me just for fun, do you know what's displacement current in Turkish? That's what I would have guessed. I would have guessed it would be yer değiştirme akımı. It turns out it's deplasman akımı. So which is which sounds like a you know supporters group, you know, like Eskişehir Spor deplasman akımı, something like that, right? So let me write down Maxwell's equations again now, and this time I hope to tell you why they are called Maxwell's equations. So Gauss's law, E dot dA is Q in over epsilon 0. Integral B dot dA is 0. Integral E dot dL is mu 0 I. No, it is not 0 I, it's minus d phi b dt. Integral B dot dL is mu 0 I in plus mu 0 epsilon 0 d phi e dt. Now, here is the thing. Here, I have currents or charges. These are called source terms. Okay. So basically, these terms in my equations tell me how to calculate the electric field somewhere or the magnetic field somewhere if I know the currents and the charges, how they are distributed in space and how they are moving. However, there are now 2 more interesting terms. As we have seen, the change of magnetic field creates an electric field in real space. That was Faraday's law. And now Maxwell is telling me something else. He's saying, hey, it's not only magnetic field change creating an electric field, but just the reverse is also possible. If I create an electric field and change it with time, that induces a magnetic field. So these are called induction terms. And what Maxwell did is he immediately realized the following. Let's say that I have no sources anywhere. All my currents and all my charges are infinitely far away. Let's say I'm in interstellar space. I don't see any currents, any wires anywhere. But if I have a magnetic field that's changing in time, Ampere's law tells me that it's going to create an electric field in space, which, because magnetic field is changing with time, electric field will be changing in time. But as a result of electric field changing, so this was Ampere's law, as a result of electric field changing, now displacement current term tells me that this is going to create a magnetic field. So the changing magnetic field will create an electric field again, which will create a magnetic field again, so on and so forth. So this whole system of equations mean that E and B can support each other without the need for charges or currents. Now, here is the next thing. What Maxwell did, and we'll sort of not really do it, but sort of tell you how it's done. Okay. From these equations, he derived the equations for this support mechanism, and he saw it must be waves. He saw that if I have an electric field which is changing in space like this, like a cosine, which is changing with time, it actually induces a magnetic field which is perpendicular to that. So he said, okay, in free space I can have these waves which have electric field and perpendicular magnetic field, and they'll have cosine variation in space, and they will move with constant speed. So what he did is he calculated, so this, the way I draw it, it's moving that way. He calculated the velocity of such waves. Now, what are the constants, what are the universal constants in my equations? Not my equations, Maxwell's equations. There is epsilon 0 and mu 0 only. And he calculated the speed of these waves, and he found them to be square root of mu 0 and epsilon 0. Now, here's the nice thing. He knew from lab experiments, from basically Coulomb's law, the value for epsilon 0. He knew by just putting a small magnet near a wire, the value for mu 0. He put in the numbers, and out comes a result which is more or less 3×10⁸ meters per second, which is very close to the speed of light. And then he said, hey, what we know as light must be exactly this. Okay. So he said, okay, there are electromagnetic waves. So there is nothing special about light. It's just an electromagnetic wave. And at the time, that was remarkable. No one had any idea about what light was. Really, I mean, Newton had this theory that, maybe it was made up of some sort of particles, and other people like Young and other people, they said, okay, it must be some wave because it shows interference and such. But no one actually tied light and electric field and magnetic field to each other. So that's a great, great achievement. I mean, he has, by working on things which have nothing to do with light at the time, like currents and charges and electric field, magnetic field, he understood the nature of light. That's why I think it's a great achievement. And here is the interesting thing. He predicted something more important. He said, hey, light is not singular. There must be other electromagnetic waves, okay, which are at different frequencies. We're seeing only a very small part of possibilities. He said, okay, so now we have wires and we can have current sources. So maybe we can do the following. We can create electromagnetic waves somewhere and detect them at some place else. So a guy named Hertz actually did that experiment first. He built what we now know as an antenna. He ran AC current through that. And some place far away, he put a wire loop and look at the voltage here. He has detected a voltage at the same frequency at his supplying from one end. So he actually demonstrated electromagnetic waves can be generated and they can be received by wires. And at the time, someone asked him, so what will be the uses for this? And he said, yeah, I can't think of anything. But actually, he was, at the time there wasn't phones, obviously, right? So he was exchanging letters with another physicist, and that other physicist said something remarkable. He said, hey, you have done an important thing. If you think about this, this invention is going to carry concert halls of Europe into every house. So everyone will be able to listen to music in their houses. And in such a world, there will be no wars. So the last part is a terrible prediction, but previous part is, this is really the basis for a lot of things we know. Radio, TV, right? Almost all our communications nowadays depend on electromagnetic waves. At some point over the last 5 years, the information that's transferred through electromagnetic waves bypassed the information transferred through sound waves. People are actually exchanging more electronic information than talking to each other. So this is actually quite nice, and this happened more than 150 years ago, and it has changed our lives completely. Let's take a 10-minute break. When we come back, we'll actually look at these electromagnetic waves in more detail. All right?